Last time, we talked about a basis set for a vector space. So now we're going to look back and see how we can find a basis set for a null space of a matrix A and a column space of a matrix A. So the first thing is, we're going to talk about what is a null space. Remember, null space of a matrix is a collection of all those elements X such that when matrix A acts upon this X, it takes to the 0 vector. Now this null space of A, guys, is a subspace of Rn, where A is a m by n matrix. Recall that we would like to find out, when we're looking at the solutions, like what are the elements of null space of A? How can we find these X's? What were we doing? We were finding the vector parametric description of the solution set of the homogeneous equation Ax equal to 0. And that actually gave us the spanning set of the null space of A. In other words, every element of X could be written as a linear combination of the spanning set of null space of A. So what we notice over here is the simplest thing we have been practicing for so long, that is the vector parametric description of a solution set of a homogeneous equation, is nothing but the spanning set of the null space of A. And the best part of this is the way we create this vector parametric description set, that spanning set becomes linearly independent. So not only that we are able to get the spanning set, but by the creation of it, it makes it linearly independent, and hence it makes a basis for the null space of A. So two things we're able to get with one little thing. So let's do some practice problems over here to find the basis for the null space of matrix A. And I'm talking of a general matrix of size m by n. So here's an example. I have this matrix A, which is a 3 by 5 matrix. Okay. Now, remember, what we have learned is the null space of A is a subspace of R5. Just a recollection of things we have done, guys. Okay. Now, we would like to find out what are the elements of null space of A. Remember, it's a subspace. That means it's a vector space. It will have infinite elements. So can I represent these infinite vector space by a few vectors? That's my idea. So what we do is, when we apply the algorithm, what do we get? This is the row equivalent matrix of the original matrix A. We get this matrix, and we find that it has 2 pivot columns, and those are the basic variables, and the rest 3 columns are the free variables. So we also, if you remember, how many elements would the spanning set have? The spanning set will have elements which are exactly equal to the number of 3 of the number of free variables. So now the thing is, we just need to find the spanning set of null space of A. And by the way it is created, it automatically becomes linearly independent. Then that means that set will be the basis set. So the only thing we have to do is find the spanning set of the null space of this matrix A, which simply boils down to saying find the vector parametric description of the solution set of the homogeneous equation Ax equals 0. Back to section 1.3. Remember how close we are every time we're going back there. Okay, so let's do the math now. Okay, I would like to find the spanning set of the null space of this matrix. Now we will work on the row equivalent form. That is, after we apply the algorithm, we get this matrix. In other words, I want to know how this X would look like in terms of the variables x1, x2, x3, x4, x5. Okay, so if you remember, just write down this two linear equations. And also at the back of your mind, remember, you're going to write down the basic variables in terms of the free variables. So we knew this was a basic variable. X1 and X3 are the basic variables. And X2, X4, X5 are the free variables for us. So this is what will give us the idea. So when you write X3 in terms of X4, X5, X2, or X1 in terms of X2, X3, X5, so it's all simple math. We just plug it in. What we have to do is write this matrix, guys. We have to write this vector X as, now this is the one we're looking for. Remember, this is in the null space of A. It's a collection of all those x's such that AX is 0. Okay, this is my X. But how will I write my X? And I play around with these variables, X1, X2, X3, X4, X5. And when I write this one, and then this is like, now from here to here, guys, from when you, this one is simply vector addition and scalar multiplication. So you write X2 plus X4 plus X5. So this is now my vector V1, V2, V3. So clearly this vector X, which is an element of null space of A, is now written as a linear combination of X2 V1 plus X4 V4 or V2, doesn't matter, guys. What these are just, variables, and X5 V3. Now clearly, by the virtue of creation of this, the set V1, V2, V3 is linearly independent. And also every element of the null space of A, which is given by X, written as a linear combination of these three vectors, that means it is spanning the span set of V1, V2, V3 is nothing but the null space of A. So we have proved the two conditions for the basis of a null space of A. And hence the set V1, V2, V3 is the basis for the null space of A. Now let's go ahead and look at the basis for the column space of A. So there's a little trick involved over here, guys. Now remember, what's a column space of A? It is the collection of all those elements B such that the matrix equation AX equal to B is consistent. Or in simple words, that the column space of A is a linear combination of all the columns of A. Now the question is, how do I find the basis set for the column space of A? So what you're going to do is, I'm going to say, hey, the pivot columns of the matrix will form the base of pivot columns of the matrix A. I'm sorry, I forgot that, guys, here. Form a basis for the column space of A. So what are we going to do? Once again, we go back to the original problem, the same matrix A which I had for the null space. I apply my algorithm and write it as this. Now remember, here we're going to look at the pivot columns. The pivot columns are the ones which control these basis set for the column space of A. So it had two pivot columns. Now these are the pivot columns for the row equivalent matrix of A. To find out the basis set for this, you go and look at this corresponding columns of the original matrix. So first column was the pivot column of the row equivalent. That means you pick up the original column of the original matrix. And similarly, the third column, which was the pivot column of the row equivalent matrix, you look at the equivalent part of the original matrix A. So these two will actually become the basis set for the column space of A. Okay, let me repeat everything, and I've written it down for you. This is how you do. You look at the row equivalent matrix of A. Now look at which of the columns are pivot columns in the equivalent matrix of A. Then look at the corresponding columns in the original matrix of A. That will become the pivot columns for the matrix A. And those pivot columns are basically becoming the basis set for the column space of A. You just have to do one simple thing. You just, in this column space basis set, just apply the row reduction, the row, row echelon form, the reduction, the algorithm, the row reduction algorithm. Just apply that, find the pivot columns. That's the only thing you have to do. And after that, you go back and look at the corresponding columns in the original matrix. Pick that up, put it in a little set, done deal. Okay, let's look at one more example for a basis set. So we want to find the basis for the column space of A. What are we going to do? So notice this is a 4 by 5 matrix. Now we all know that the column space of A is what? It is a subspace, just to, keep on reminding what we're knowing, R4. Okay, so what we do is we apply the algorithm, we get the row equivalent form, so we get 3 pivot columns here in the row equivalent matrix. And then we go back and look at what are the corresponding columns. It is the first column, the third column, and the fifth column. These 3 columns will become the basis set for the column space of A. And that's it. We do not need to do anything here. And remember, we talked about a rank of a matrix way long when we talked about pivot columns and stuff like that. So the rank of a matrix is nothing but the number of pivot columns of a matrix. As there are 3 of them, so the rank of A is 3. A very, very important observation, and which will help you when you do problems, and if there are mistakes, you need to come back to this observation. How many pivot columns are going to be in the basis set of a column space of A? The number of pivot columns of a matrix is equal to the number of vectors in the basis set of column space of A. And the number of free variables in a matrix is equal to the number of vectors in the basis set of null space of A. And that is the most simple. So in other words, if you see a matrix which is already in the row echelon form, and just looking at that matrix, you can automatically say, oh, that will be the number of vectors in the basis set for the column space, number of vectors of the basis set of the null space of that matrix A. Very, very. You don't even have to do any kind of extra work. Just look at the matrix. If it is in the row echelon form, use this observation from section 4.3, page 17, down D. Okay, now let's look at some important viewpoints of the basis. When we're having a spanning set theorem, the deletion of vectors should stop when the set becomes linearly independent. And if you delete one more additional vector from that linearly independent set, then the vector no longer spans the vector space. So you have to, it's a very, very, very dicey situation. You just go remove the vectors till it becomes linearly independent. And that leads to 2 important statements. That the basis set is a spanning set which is as small as possible, and basis set is a linearly independent which is as large as possible. Okay, so guys, some practice problems. So these practice problems are from the book of Lay, 5th edition, which is 9, 10, 13, and 14. And we already know the solutions are in slater.com. Thank you.